Welcome to another Mathologer video. Let me start by showing you something very cute. X plus 2 cubed? Cute? Okay, here's a kitten. Definitely cute, but bear with me. X plus 2 cubed is also cute. Let's expand. 6, 12, 8. Numbers ring a bell? No? How about now? Aha! A cube has 6 2D faces, 12 1D edges, and 8 dimensionless, 0-dimensional vertices. Damn, no 0 inside. Well, actually there is. X to the power of 0 is equal to 1. And when it comes to solid cubes, let's not forget the 3D interior of the cube. Very nice, isn't it? Think we're onto something? Or is it all just a strange coincidence and I'm just leading you on? What do you think? Of course there's something there. Lots and lots and lots. The mathematical superheroes Euler and Schläfli, Iron Man, you heard right, hyperspace, one of the most beautiful formulas in maths, the shape of the universe, all intricately connected to this simple observation. Lots of amazing insights to look forward to, so let's go. Okay, if there's anything here, then all those exponents should stand for dimensions. So it's a reasonable guess that this 3 here somehow has to do with the fact that we're dealing with a 3-dimensional cube. Okay, so let's check. Let's try a different dimension. What's the 2D counterpart of a cube? What's a 2D cube? Well, a square, of course. Expanded, that x plus 2 squared on the left gives this. Yep, that works. One brown 2D solid square, 4 aqua edges and 4 red vertices. Just to be sure, let's check another dimension. What's a 1D cube? That doesn't sound very cubey anymore, does it? But if a 1D cube is anything, it's got to be this. Just a skinny little line segment. And yep, those numbers pan out again. But why stop here? What about a 0-dimensional cube? And mathematicians wonder why people think they're weird. Anyway, there's nothing in 0 dimensions except for a single point. So a 0D cube got to be that point. And yep, that works too. Very nice. 0, 1, 2, 3, what's next? 4, of course, right? 4. What's a 4-dimensional cube? Well, whatever it is, we now have our trusty formula to guide us. According to our formula, a 4D cube should consist of 16 vertices, 32 edges, 24 faces, and so on. Now, using the binomial formula, which you may remember from school or my last video, we can write down the general formula. So just put 6 or 66 or 666, whatever you like. And so, whatever an n-dimensional cube might be, if there's a God, the number of m-dimensional bits in an n-dimensional cube should be the general coefficient in this expression, that one here. Very pretty formula, don't you think? Now, just in case you're a bit rusty on your school maths, the bracketed expression is called a binomial coefficient. It's the number of ways in which you can choose m objects given n objects to choose from. In terms of factorials, the binomial coefficient looks like this. It's all coming back now. I sure hope so. Before going on, let's look at a simple case that we know and do a quick check that this formula really works and how it works. Always a good idea. So, what's the number of 1D bits, that's edges, in a boring old 3D cube? That's 12, of course. And what does our formula say? Well, we're interested in the 1D bit, so m is equal to 1. In a 3D cube, so n is equal to 3. Okay, now, engage Algebra Autopilot. "12 edges, works. Okay, all in order. We have our higher dimensional cube formula, but does it really tell us anything new? Are there really higher dimensions to throw cubes into? Yes and yes. There really are higher mathematical dimensions, hyperspace, and there really are 4D, 5D, 6D, etc. hypercubes. And yes, by expanding x plus 2 to the power of n, you really do get the correct numbers of bits and pieces in these hypercubes. And of course, all will be explained. Now, chances are that on your YouTube journeys, or maybe even your library journeys, for the older guys, you've already encountered ghostly shadows of these hypercubes. For example, I'm sure many of you will be familiar with this iconic 3D shadow of a 4D cube. This shadow from the 4th dimension already made an appearance in my video on how to solve the 4D Rubik's Cube. There you actually interact with the 4D Rubik's Cube via its 3D shadow. You should definitely give this a go. A lot of fun. This mysterious shadow also made 2 appearances in the Marvel blockbuster movie Iron Man 2, in the scene where Tony Stark flips through his father's notebook. There's one of those, and the second time on the next page. Now, the supersymmetric diagram here is another shadow of a 4D cube. There's a shadow of a 3D cube, a 2D cube, a 1D cube, and a 0D cube. Now, can you spot anything else on this page that looks familiar? Yep, there's our formula for the number of MD bits in an ND cube. Now, one of my main missions today is to turn you into hypercube masters and prove this bits and pieces formula, to prove that the x plus 2 to the power of n expansion trick really always works. But before I get to that, let me show you some very pretty consequences of that formula. Here's an idea. Why don't we substitute some numbers for x? What would be a good number to try here? How about 1? Let's see what happens. Well, in the brackets on the left, we get 1 plus 2 equals 3. And on the right, all the powers of 1 are equal to 1, and so we can just zap them. Now, the right-hand sides are just the sums of the edges and vertices and so on. So what this tells us is that in total, an ND cube consists of 3 to the power of n bits and pieces. For example, for our 3D cube, we get those familiar numbers 6 and 12 and so on. And it all adds up to 3 to the power of 3 is equal to 27. In a square, it's 3 squared is equal to 9, etc. Cute, isn't it? And probably not something most people would have noticed or considered to be of any significance. That worked pretty well, so why not try again? What other values of x come to mind? Well, x equal to 0 is always worth a trot, but you can easily check for yourself that nothing interesting comes from this choice. If you do this, everything kind of wipes out, right? It turns out the most interesting choice is x is equal to minus 1. Then, in the brackets on the left, we get minus 1 plus 2, that's just 1, and raising 1 to any power still just gives 1. Okay, what about on the right? Well, even powers of minus 1 give 1, and odd powers give minus 1. So we get alternating plus and minus signs in the sum. There we go. Interesting how these numbers on the right cancel out, isn't it? Still, I hear asked, what's the big deal? Well, let's see. First, those leading ones on the right, which correspond to the highest dimensional blob, are common to all the equations. Since they're not special in any way, let's move them out of the way and move them over to the left. Okay, there's 0, there's a 2, that becomes a 0. 2 and a 0. 0, 2, 0, 2 forever. I'm sure some of you will have had an aha moment by now. But let's keep on going until everybody is ahaing. Remember, red stands for the number of vertices, aqua for the number of edges, brown for the number of faces, and gray, well, we haven't called it anything but 3D blob so far. Let's give it a more respectable name. Let's call it a cell. 0 is equal to 0 at the top, not much of an equation, so let's zap that one. Also, we can make these equations look nicer by reshuffling them back to front. Now we're getting somewhere. For example, the third 3D equation tells us that the number of vertices minus the number of edges plus the number of faces of a cube is equal to 2. A lot of you will recognize this formula, and many of you will also know that what's amazing is that the formula works not only for our cube, but for all convex 3D polyhedra. That is, vertices minus edges plus faces equals 2 for any convex, so no indentation, solid object whose surface is made up of a finite number of polygon faces. For example, for this dodecahedron. Here the number of vertices, edges and faces are 12, 30 and 20. And 12 minus 30 plus 20 really is 2. And for this pyramid, we have 5 minus 8 plus 5, which is again 2. V minus E plus F is equal to 2 is called Euler's polyhedron formula. There, the Swiss mathematical superstar Euler, the man with the towel hat, strikes again by discovering another one of the top 10 most beautiful and influential formulas in mathematics. Next time you buy an elaborately cut diamond for your beloved, and she won't be happy unless you also tell her how many vertices, edges and faces it has, remember that you only have to count 2 of these numbers. The third follows from Euler's formula. What about our other 0202 formulas? Well, believe it or not, these work for all convex polyhedra in all dimensions. This was discovered by another Swiss mathematician, Ludwig Schläfli. No towel hat, but man, that beard. If I was a hairman, I'd be jealous. Okay, can we actually prove that the Euler-Schläfli formulas really always work? Well, the 1D equation is super easy. The only convex 1D poly thing is the line segment. It has two vertices. Proved! Neat! I can tell you're really impressed, right? No? Okay, well then let's up a dimension. The 2D formula is v minus e is equal to 0, which says that for convex 2D polyhedra, the number of edges is always equal to the number of vertices. Well, that's also easy to see. A convex 2D polyhedron is a 2D blob surrounded by a necklace of vertices and edges. And since the vertices and edges take turns along the necklace, there are equal numbers of them. Proved again. We're on a roll. Up one more dimension. Okay, so now we're back to Euler's formula for a 3D blob. And proving Euler's formula is a lot trickier. But a methodologized sketch of one particular proof does not take more than a minute or so. And so let's do it. Take an arbitrary convex 3D polyhedron. I'll illustrate using a cube again as our example. Of course, we know exactly what we'll get with a cube, but it should be pretty clear that the same process will work with any convex 3D polyhedron. We start by placing our 3D blob in space so that one of its faces on top is parallel to a plane. Then we place a 3D light source close to this face, and by doing so we create an intersection-free shadow on the plane. The resulting network has the same number of vertices, edges and faces as the original shape, well, with one proviso. I think it's clear that we get the same number of vertices and edges in terms of the faces of the cube. It's also clear all have counterparts inside the network, except for the one we shine the light through on top, right? That face of the cube corresponds to that face of the network, and that one corresponds to that one. On the other hand, the shadow of the top face is the whole network. Now, to compensate for this one missing face inside the network, we simply count the outside of the network, which currently does not do anything, as the missing face. Slick move, huh? So in our example, those are the 6 faces of the network. There, faces 1 to 5 are inside the network, and face 6 is the outside. Main thing, we have 6 faces, just like in the cube we started with. Now, we modify the network by suitably adding and subtracting vertices, edges and faces. First, we chop up every face into triangles by adding some edges, like this. There, 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 there. Okay, then we prune away from the outside like this. Okay, there, 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 prune, 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 until eventually we end up with a triangle. Now, at each step of this process, we're changing the network. And so we're changing the numbers of vertices, edges and faces. But, and this is the nifty part, it is easy to see that with each step, the quantity v minus e plus f does not change. So for all the networks that we create along the way, the quantity v minus e plus f is the same. But that means that the v minus e plus f of our original blob is the same as the v minus e plus f of the triangle. And what is the v minus e plus f of the triangle? Well, it has 3 vertices, 3 edges, and 1, 2 faces. And so the v minus e plus f of a triangle is equal to 3 minus 3 plus 2 is equal to 2. And the exact same argument works no matter which 3D blob, which convex 3D polyhedron we start with. The v minus e plus f for all convex 3D polyhedra is equal to the v minus e plus f of a triangle, and so is equal to 2. Now, that's a very pretty proof, isn't it? A proof that you won't forget for the rest of your life, I hope. Again, what makes this proof work is that we shadow squish our 3D blob into a network, and then by a number of mini steps, we transform the network into a triangle. And both the squishing and each of these mini steps keeps the v minus e plus f the same. I said the sameness is easy to see, but let's have a look at one such mini step to see how it works. So, for example, at this stage of the process, we're about to prune away the vertex and the edge indicated by the arrows. But what's the effect on v minus e plus f if we remove one vertex and one edge? Well, minus 1 minus minus 1, that's 0, and so the net effect is 0, and we can be sure that the new network has the same v minus e plus f as the original network. Very nice, isn't it? And very similar cancelling arguments work for all the mini steps in the argument. Bit of a challenge for you. Go through the individual steps of our transformation and convince yourself that the v minus e plus f really never changes. Of course, for a completely rigorous proof, there are still i's to be dotted and t's to be crossed, but there's no hidden trickery. Promise. What about proofs for the higher dimensional formulas? For example, the 4D formula is supposed to apply to things like the mysterious and monstrous 4D 120 cell with its 600 vertices, 1200 edges, 720 faces and 120 cells. That's the shadow over there. 600 minus 1200 plus 720 minus 120 equals 0. Works, at least for that one. Well, the 4D and higher dimensional formulas can also be proved by elaborate squishing and pruning, just as we did prove Euler's formula. A lot harder to keep track of all the multidimensional bits and pieces, but basically the same thing. Now, before I move on, let me mention that these formulas form the starting point of a lot of very deep and powerful mathematics. In particular, the left sides of these formulas can be calculated for many mathematical spaces apart from convex polyhedra. And the resulting numbers tell us a lot about these spaces, the possible shapes of the universe we live in, and so on. Great stuff, and something that my colleagues and I really get very excited about. Now I'd like to finish off the video by proving that our x plus 2 to the power of n expansion trick and the Beardman formula really work. I'd also like to give you a hands-on intro to high dimensional cubes and their spectacular shadows. Again, this formula is supposed to give the number of m-dimensional cubes in n-dimensional cubes. As you'll see, it's actually surprisingly easy to prove, and the proof is very pretty. That beard. This is great. Sick of cubes yet? Not me. I love cubes and I could go on for hours. But I can see that some of you are flagging a little, so okay, here's another kitten, this time in a cube. Very cute. Feeling revived and ready for an ultra satisfying aha experience? It's a bit of work, but 100% worth it, and by the end of it, you'll all be hyperspace masters. Okay, when studying cubes, it makes sense to focus upon some particularly nice example, like the one over there. Its vertices are all the points whose coordinates are either plus or minus 1. Nice and symmetrical. The corresponding 1- and 2-dimensional cubes are these. There, plus minus 1 everywhere for all the vertices. And what about the higher dimensional counterparts? Well, these hypercubes may not exist in any physical sense, but mathematically there's absolutely no problem to define them in a meaningful way that meshes in and extends perfectly what we observe in dimensions 0, 1, 2 and 3. For example, we declare the vertices of our prototype 4D cube to be all the points in mathematical 4D space with these plus minus 1 coordinates. Obvious, right? There is no other reasonable way to do this. Then, how many vertices are there? Well, there are 4 coordinates, each of which is either a plus 1 or a minus 1. And so, in total, our 4D cube has 2 times 2 times 2 times 2 is equal to 16 vertices, just as the Beardman formula predicted. In exactly the same way, an ND cube has to the power of n vertices. Now, some pairs of vertices are connected by edges and others are not. What's the rule in the lower dimensions, which we can then use to also define which pairs of vertices are supposed to be connected by edges in dimensions 4 and up? It's really quite natural and simple. Let me show you. Okay, here are 2 vertices connected by an edge. When you move from one vertex to the other, along the edge, exactly one of the coordinates changes. In the case of the edge over there, since we are moving parallel to the x-axis, It's the x-coordinate that's changing. And that's true in general for all the lower dimensional plus minus 1 cubes. Two vertices are connected by an edge if and only if they only differ in one coordinate. Here's another example. There, all coordinates the same except for the last. Now we use the same rule to define, we're really playing God here, we're extending what's there in lower dimensions, when two vertices are connected in higher dimensional cubes. For example, here are three vertices in our 4D cube. The vertices on the right only differ in the last coordinate and therefore are connected by an edge. The top 2 points only differ in the second coordinate and are also connected by an edge. But there is no edge between the bottom 2 points because they differ in 2 coordinates. Easy, right? So now we know what the 0D and 1D bits of higher dimensional cubes are. That's the vertices and edges. What about the 2D bits? That's the faces. 3D bits, the cells, and so on. Well, that's also easy. To get the general super rule, let's rephrase our edge rule like this. Two vertices form an edge in the ND cube if n-1 coordinates are the same, right? Different in exactly one coordinate is the same as saying that the remaining n-1 coordinates are the same. Let's type this out. There, two vertices of an n-dimensional cube form a 1D bit if they share n-1 coordinates. Okay, actually the 2 in front really stands for 2 to the power of 1. Now to get the rule for faces, just replace all 1s by 2s. For example, over there are 2 to the power of 2 is equal to 4 vertices that form a face of a 3D cube. So here the n is 3 and 3 minus 2 equals 1. And indeed all these 4 vertices have one coordinate in common, right? The z coordinates are all the same. Works. In the most general form of the rule, the 2 gets replaced by an m, and now the whole thing reads like this. Cool. And based on this rule, it's actually not very hard to show that the Beardman formula is really true, which then implies, by the binomial formula, that the x plus 2 to the power of n trick really always works. Maybe give this a try yourself. As I said, proving the formula like this is pretty easy, but sadly, proving like this is also a bit boring. My friend Tristan had a better idea for a much more direct and visual proof, an absolute killer to mythologize, but totally worth it. Have a look. Beautiful the way our cubes grow from a single point, right? And of course, you can go on like this algebraically to grow all our high dimensional cubes. Now, let's start again from the beginning, but this time we also grow the numbers of bits and pieces in parallel. Sounds intriguing, doesn't it? Well, it definitely is. Have a look. There, that's the point again, the 0D cube. It consists of just one vertex. And on the right, we record this number fact as we did at the beginning of the video. Very pretty, right? And the algebra carries on all the way to infinity. And it gets even prettier. Again, one more time from the start. Okay, let's call the polynomial expression that counts the bits and pieces in the ND cube Pn. Then this is P0. Now let's calculate P1, the expression for the 1D cube again. Important here is that the second expression is the first expression times x. Let's add up. First on the right, we've already done this. On the left, we have one p0 plus another p0, that's two p0s, plus x times p0, so that's x plus 2 times p0. So that means that p1 is equal to x plus 2 times p0. Aha! Can you see where we are heading with this? Almost there. Anyway, with exactly the same argument, we can now show that p2 is x plus 2 times p1, that p3 is x plus 2 times p2, and so on. And here's the finale. Aha! And that's why the x plus 2 to the power of n trick works. How satisfying was that? Well, thanks again to Tristans for this very beautiful argument. Very pretty and sort of a natural place to stop, but I just could not resist. I just had to add another mini chapter to round things off. It's all very well to define these abstract high-dimensional cubes and to make sense of them in the way I described. But how can something that does not exist in the physical sense have a solid 3D shadow? To finish off, let me explain this little miracle to you. The explanation is based on our special ±1 cubes and the shadow picture that I and Iron Man showed you earlier. In this shadow picture, we see a 3D cube being projected onto a 2D plane using a light source above this plane. The shadow is that square inside a square network, which is clearly the 2D counterpart of the cube inside a cube 4D shadow that we're trying to explain. Now, I created a projection picture in Mathematica. Of course, on the computer, all this projecting and visualizing is all done in terms of coordinates. Now, in this picture, the z-axis is vertical, and I've chosen the light source to be the point 003 on the z-axis. The shadow is formed on a plane parallel to the xy plane at depth z is equal to -3. Now, to mathematically create the shadow of the 4D cube, we simply have to add one dimension, a w coordinate. Then the process is essentially identical. So replace the 003 coordinates of the light source by 0003. Replace the ±1 coordinates of the 3D cube by the coordinates of the 4D cube. And replace the 2D plane by the 3D hyperplane w is equal to -3. Then push the execute button and voila, as if by magic, the shadow of the 4D cube appears out of nowhere on your computer screen. Let me show you the programs for the 2D and 3D shadows side by side to drive home the point how easy it is to create these nice 3D shadows of 4D cubes. As you can see, apart from putting in some more vertices and replacing the occasional 3x4, there's not much of a difference between the two programs. If you want to play around with these programs, you can download them via the link in the description. Real mathematical magic, isn't it? Well, that's it for today. I hope you enjoyed today's selection of mathematical miracles. As a special reward for everybody still watching, here is some extra magical shadow play featuring our 3D and 4D cubes spinning in space. Enjoy. Until next time.